So for today's session, we'll cover the content of week 12. So as you have already seen the video lectures, the topic of discussion in the week 12 was on microwave communication systems and their application areas. So the video lectures were on overview of radar. So as you all know, the radio detection and ranging systems were discussed in the very first lecture, and then followed by a lecture on cellular communication. And towards the last, the discussions were on satellite communication and applications of microwave. So I have a few questions in this, mostly in the area of radar and cellular communication, and a few on the applications and satellite also. So we'll start with radar in the beginning. We'll start with radar because that's a very fundamental concept known to most of you. So as you know, radar is nothing but radio detection and ranging system. Um, so the basic idea of a radar or basic purpose of a radar is to estimate the distance to a particular target, or calculate the velocity of that target, uh, and so on and so on. There are a few things. So to give you a fundamental refresh of the concept, all of you know that say for example you have a transmitting antenna, and at some distance d you have a target. Okay, so you send in some signal to the target, you expect some backscattered signal from the target, and so the total distance, the round trip distance traveled, can be written as 2d. Okay, assume that there is a time delay between the time when, say, at time t1 a signal was sent, and at time t2 the signal, the backscattered signal was received. So that is the time difference between these two is called as the time delay. With the help of the fundamental relationship of distance, time, and velocity, we can write it in as 2d is equal to c times td. Okay, 2d is the total distance traveled, c is the velocity of the electromagnetic wave, and td is the time delay between the signal which is sent and which is the backscattered signal reception time. So if you know, you already know what is c, the distance, the velocity of the electromagnetic wave. And if you know the time delay between the sending in of the signal and the reception of the backscattered signal, then you will be able to estimate the distance to the target. So this is one of the very fundamental purpose of a radar. Now, let me talk about types of radar. One is a monostatic radar and the other is a bistatic radar. In a monostatic radar, you have how many antennas? So let me just discuss this question so that you can answer the question also. The radar in which both transmission and reception is done using the same antenna. Is it a monostatic radar, a bistatic radar, or monopole radar, or dipole radar? Which is the type of radar? I request you to type in the chat, or you can even unmute and answer. So in which radar the antenna will be same? I mean, the reception and transmission is using the same antenna. So the right answer is monostatic radar. Okay. So in a monostatic radar, you have same antenna. Okay. You have only one antenna which is being used for transmission and reception. Whereas in a bistatic radar, you have two different antennas. One for transmitting the signal and the other for the reception of the backscattered signal. Okay. Now, let's see the next question that will explain. Let me see what is that. For applications like missile fire control, bistatic radars are used. Is it a true statement or a false statement? In the application of missile fire control, bistatic radars are used. Please type in the answer in the chat. What do you think? So bistatic radar, I can give you a clue on that. What do you mean by a bistatic radar? For example, or when we require it, okay? Whenever you need a continuous transmission and reception of the signals. So you are continuously transmitting and continuously receiving the signals, then you require a bistatic radar. Okay. In missile fire control, the target is illuminated with one antenna or signal from one antenna, and the reflected wave or the backscattered signal is received by another antenna in the radar. Okay. So in application for missile fire control, we use the bistatic radar. So this is a true statement. Okay. Now coming to the next question. So before moving to the next question, I would like to explain a little bit on the radar cross section. So, and in general, what is say suppose you have a transmitting antenna. You have a transmitting antenna which will transmit a power PT, say PT, and the gain of this antenna is G, and your target is at some distance R, for example, at a distance of R, and you are sending a signal with wavelength lambda. Okay. Now, the signal is going to hit the target, and once the energy is being once it is hit on the target, there will be scattering in all directions. Okay. A part of this scattering, which is being collected back. Okay. A part of the scattering signal is being collected back. Some part is not being collected. So what I'm trying to say is some part is being collected by the antenna. Okay. Receiving antenna, and the received power can be written as PTG square. So gain, the transmission and reception. So you have gain of the transmitter and gain of the receiver. That is why it is G square lambda square sigma divided by 4 pi the whole cube r raised to 4. So I haven't mentioned this parameter sigma. So sigma is called as radar cross section. So this will so basically what is radar cross section? That is a property of the target. Okay. So what is that radar cross section? It is the ratio of scattered power in a given direction to the power incident on it. Okay, so how much some power is incident on the target. Okay, some power is being scattered back. So if you take the ratio of scattered power in a given direction, say I am taking the scattered power in a particular direction, that power, scattered power in in one direction to the incident power, that ratio is called as the radar cross section. Okay. Now, let me go to the question. The term radar cross section defines the scattering ability of the target, power radiating ability of the radar, amount of energy scattered by unwanted objects, cross section of radar area through which the energy is emitted. Now, I request you to answer this question based on the idea which I have given. What is radar cross section? Yes, radar cross section is giving you the scattering ability of the target. So, as I said before, it is the ratio of scattered power in one direction to the incident power on the target. Okay, so that is one question. Okay, now let's move to the next question. In military applications, the radar cross section of the vehicles is minimized. Is it true or false? Okay, if your answer is true, I have another question for you. What do you mean by reducing the radar cross section or minimizing the radar cross section?
Hello, madam.
Yes, please.
For anything we are going for that advanced miniaturization is very important, no, madam. For that reason only I answered.
Okay, okay, okay. So let me tell you what I spoke in the previous question. I spoke about the scattering ability. So uh, radar cross section is nothing but the scattering ability. If something is being scattered from the target, okay, that is being denoted by sigma. Okay, in military application, sigma has to be reduced. That means scattering. That means the power scattered from the vehicle has to be reduced. So if you reduce the power scattered from the vehicle, then it will not be detected by the other country. Say, when we talk about military application, if a aircraft is being moving to the other country, the we want this aircraft to be undetected. Okay, we don't want this aircraft to be detected by others. So for that, what is to be done? It has to be undetectable. So to make it undetectable, that means scattering should be reduced. That means sigma should be reduced. So that is the idea of reducing the radar cross section of vehicles in case of military application. I hope you understood the concept. So lower the radar cross section, there will be less power scattered by that object. Therefore, that object, whichever the object is, it will not be detected. So that's the application in military area. Okay, now let's move to the next question. So this is about different types of radars are given: pulse radar, Doppler radar, cross section radar. Which among these will determine the target range by measuring the round trip time of a pulsed microwave signal? So I spoke in the beginning, how do you measure the range or the distance to the target? By knowing the round trip time or the round trip time delay. Time delay means the time taken for the signal to go to the target and then come back. Say that is TD. Then TD is the time delay. And suppose distance is 2D. As I said, 2D is C into TD. So D can be found. D can be found. So such a radar is known as pulse radar. So we are sending in pulses. Okay. So once you send in a pulse at time T1, okay, and you try to receive, so this is being sent at T1. After some time, you get a backscattered signal that is at time T2, okay. So the time difference between these two will be calculated as time delay, okay. So this is known as a pulse radar. Now, Doppler radar. Let me come to what you mean by a Doppler radar. So to explain about Doppler radar, I would like to use this figure. So as you can see here you have an antenna. Okay. You have an antenna. This is some source. Okay. From this source, this is your source which will generate a high frequency. So that high frequency is F0. Okay. And from F0 is coming here. So there is a circulator. I hope you remember what do you mean by a circulator. So say suppose this is port 1, this is port 2 and port 3, and you have seen the symbol of transmission. As you can see, a circulator will have a transmission from 1 to 2 but not from 2 to 1. Okay, always from 1 to 2, and anything input at 2 will be transmitted to 3. Again, anything input at 3 will be transmitted to 1. Okay. So that is the working of a circulator. So what happens? The input's frequency at 1 will be transmitted to 2. And this 2 will be sent to the antenna. And the antenna will be sending it to the free space. In free space, it is F0, which is your transmitted signal. Okay. This is your transmitted signal. And this is the target. Okay. Wherein you have indicated a radar cross-section sigma. Now, after hitting the target, there will be a backscattered signal. Okay. And if there is a frequency shift, if there is a change in frequency for the backscattered signal, okay, why will there be a change in frequency? Because the target is moving at a velocity v. Okay, suppose the target is moving at a velocity v, then there will be a shift in the frequency of the backscattered signal. So F0 will become F0 plus minus Fd. Then coming back, it comes to which port? Port number 2. Once it is incoming to port number 2, it gets transmitted to port number 3. And what happens at port number 3? At port number 3, the frequency is F0 plus minus Fd. Now, this is a mixer. At mixer, what happens? It is being mixed with F0 and you will extract Fd, the Doppler frequency. Okay. And the Doppler frequency will be filtered and further amplified and then displayed. Okay. So this Doppler frequency will be calculated. So if you know the Doppler frequency, you can calculate the velocity using this equation. So what do you mean by velocity? It's the velocity of the target. I told the moving target. The target is moving. Using a radar, you send a signal. The backscattered signal will have a shift in the frequency. You take out what is that shift. You want to calculate the velocity of the moving target. You use this equation. Fd into C divided by 2 times F0. Please note this equation. This is really very useful for solving the assignment question. So velocity of the moving target can be calculated as Doppler frequency shift multiplied by c. C is the speed of light, and 2 divided by 2 f naught. F naught is the transmitted signal frequency. I hope this is clear. If there are any doubts about the Doppler radar, kindly ask. Okay. If there are no doubts, I have a question to ask. Please answer that. So, the you have seen a circulator over here. So, the circulator, is it helping to use one single antenna for transmission and reception?
No, madam. Why? Because circulator is only one direction, no? 1 to 2, 2 to 3.
Yes. So, but
Only one direction.
okay.
Okay.
So my question, I think you did not understand my question. So what I am trying to say is, this is the input signal, okay, input frequency. So that input frequency is coming to antenna, one antenna, okay. Now the backward signal is coming, backscattered signal is coming to the antenna. Antenna will give it to which port? Port number? Can you tell me which is the port number? Backscattered signal is port number 2, right? So, so what does the circulator do? It will not mix up with the input signal. Circulator will make sure that the backscattered thing will go to port number 3, not to port 1. Okay, it will not mix up. So that is the use of a circulator. So circulator will help such that the input frequency is sent into the same antenna, and the output the backscattered signal is also coming through the same antenna, but being taken to another port of the circulator and further used for the Doppler frequency extraction. Okay. Okay, now I have a question. This is a small numerical. I request you to solve this question. So the question is like this: the pulse radar operating at a frequency. So you have a frequency 10 gigahertz, and it has an antenna with a gain of 28 dB. So the gain of antenna is 28 dB. The transmitted power is 2 kilowatts. So PT is 2 kilowatts. If it is desired to detect a target of cross section 12 meters square, okay. So target of cross section, that means the radar area of which sigma is 12 meters square. The minimum detectable signal is minus 90 dBm. Okay, so you are sending in some signal at a frequency 10 gigahertz. The antenna gain is given. Transmitted power is also known, and it is hitting the target at some area. From some area, it is being transmitted back. Backscattered signal is coming back. It should be at least minus 90 dBm to get detected. Okay, so minimum detectable signal is minus 90 dBm. Now, what can be the maximum range? Okay, what can be the maximum range to the radar? Now, can we use the equation PR is equal to PT G square lambda square? So I hope you remember this equation when this one. PT G square lambda square sigma by 4 pi cube 4 pi the whole cube r raised to 4. Okay. So in this equation, you know PR, PT, G, lambda, sigma. You are going to calculate what? R, maximum range. Now, the only point here is whatever in dB has to be converted to linear so that you will use it in this equation. Okay, so how do we convert the gain 28 dB? So the simple thing is 10 log x is equal to 28. So x is equal to 10 power 2.8. 10 power 2.8 will be the linear value of the gain. Similarly, this is in dBm. How do we convert? PR is equal to 10 log of x is equal to minus 90 dBm. So dBm means dB in milliwatts. Okay. So whatever answer you calculate as x will be in milliwatts. That is the idea of dBm. Okay. So let me take it. X is equal to 90 and 10 will cancel out. So x is equal to 10 power minus 9 milliwatts. Okay. I hope this is clear. Any doubts, please ask. So I can write PR as 10 power minus 9 milliwatts. So now the step is just to substitute everything and find out what is R. I request you to do this calculation and let me know if you have any doubts. How do I calculate the PR or how do I calculate the gain? I mean, how do I convert from dB or dBm to the linear? So I'll give you some time to try this calculation. Okay, so are you telling the final answer for R? Okay, okay, that's the right answer. R should be 8114 meters. Now let's move to the next question. Actually, this is already being asked. Let's go through it. In a Doppler radar system, circulator allows the use of antenna for transmission as well as reception. So as we have discussed already, it's a true statement. Circulator is being used. It allows the antenna to be used as the same antenna to be used as a transmitter and a receptor. Now moving to the next question. For a monostatic radar with a transmit power PT, so let us denote it like this, PT. Received power at a distance R is PR. The target now moves to a distance 2R. What will be the received power? PR dash. Okay. So let's look at this equation again. So if you look at this equation, have you noticed the received power PR is 1 proportional to 1 by R raised to 4. That means if the distance increases, the received power will reduce. Okay. So the proportionality constant is with 1 by R raised to 4. So keeping this in mind, so PR is proportional to 1 by R raised to 4. So here what is the question? For a radar, it is receiving the power at a distance R, it is PR. Now suppose if this R becomes 2R, okay, suppose if this R becomes 2R, what will be PR? So PR will become PR dash. Okay. Now tell me what will be PR dash. Yes, right answer. So PR dash will be 1 by 16 times PR. Okay. So the right option is option D. Okay. Now I have another question. Okay. A radar transmits a power PT, that is 2 watts. Antenna gain is 30 dB. Operating frequency is 2 gigahertz. If the power received at the receiver is minus 60 dBm, when the target is at a distance of 1 kilometer. So how do I take? R is 1 kilometer or 1000 meters I can take in meters. What is the radar cross section? Use the same equation which we have used before. PT G square lambda square sigma divided by 4 pi the whole cube into R raised to 4. So I hope you remember. This is very important equation. When it comes to radar, there could be many questions based on this equation. So I request you to try finding sigma. You are given with rest of all parameters. First of all, tell me what is G and PR in linear terms. So let me start with G. Can you convert this G in dB to G in linear? Gain in linear value of gain, 30 dB. Use the same technique which I have used in the previous question. Ten log x is equal to 30. So what is x?
What 1,000?
Yes. So that gain is 1000. Okay. Now, can you tell me what is PR? Again, 10 log x is equal to minus 60. So dBm. So remember it is in milli.
10 power minus 6, ma'am.
So x will be 10 power minus 6 milliwatts. Don't forget the milli. Okay.
Milli.
So 10 power minus 6 milliwatts, or I can say 1 nano. Oh, sorry. 1 nanowatts. Okay. Now substitute and find sigma. PR into 4 pi the whole cube r raised to 4 divided by pt g square lambda square. Yes, the right answer is 44.097. Your answer is right. So the radar cross-section unit will be meter square. Oh, so now I have, I think the questions on radar is over. Now we will move to a few questions on cellular communication. So before I start with questions on cellular communication, I would like to give a brief on the cellular communication. So as you know, we always want to have a better capacity or higher system capacity with a limited radio spectrum. So in cellular system, general terminologies are all known. Say this is called as a base station. Suppose you have whatever you have a mobile or something, we call it as a mobile station. So that means it is moving. Okay. So from the base station, the signal is being sent to the mobile, and from the mobile the signal is being sent to the base station. So that is how we do communicate on a wireless or cellular communication channel. And multiple, so this base station will act as a central unit to signal for the signal transmission to multiple mobile stations. Okay. So this downlink and uplink is nothing but you send signal in one direction, it is called as uplink. That means from the mobile station to base station it is uplink, and from base station to mobile it is the path is called as downlink. Okay. Now suppose you have two cells, two adjacent cells. Okay, so this is indicating one cell and this is the another cell. So in each cell you have base stations, okay, to which there will be communication. Suppose very simple example, when you are talking and you are traveling. Okay, so the mobile station is having a movement. So mobile, suppose your mobile station was under the coverage of this base station 1 and this is base station 2. Now the mobile is being moving on in this direction. Okay, now this is being, as the distance from the base station is increasing, the received power will reduce. Okay, and this mobile is entering this cell. Imagine it is entering the next cell. So distance from the base station 2 is less compared to distance to the base station 1. So there will be more signal from the base station 2. So there will be a switching between the base station 1 and base station 2 for this particular mobile. So that is called as handoff. Okay, signal handoff. So that is why sometimes when we are traveling at some distance, we lose contact to one base station and we get into contact to the other base station. That is when we have a small breakage of the signal at that point of time, when there is a handoff. Okay, so I hope this is understood. So the signal to noise ratio will depend on the transmitted power, the distance to the base station, etc. So any doubts with respect to this explanation of cellular communication, you please ask, or I'll move to some of the questions. Okay, so let us start with a few questions so that we'll understand the concept of cellular communication slowly. Okay, the cellular concept replaces many low power transmitters to a single high power transmitter. Okay, so if you understood the concept of cellular communication, you can imagine there are multiple base stations, right? So there are multiple cells. Okay, cell A. So in a particular area, for example, you take a particular city. Okay, in a city you have multiple cells. So the whole geographical area of a city is being divided into multiple cells. Say there is cell A, cell B, C, D, E, F. Okay, multiple cells. in each of these cells you have different base stations. Okay, and all the mobiles in one cell is being covered by one base station, which is the base station A. Then if you go to the next cell, that is being covered by base station B. Okay, and so on. So instead of having a single high power transmitter, okay, which will transmit to the whole city, okay, instead of having a very high power transmitter which will transmit to A, B, C, D, E and F, instead of that you have a low power transmitter only for A, another low power transmitter only for B, another low power transmitter only for C. Okay, so that is the idea of this question. Cellular concepts replace many low power transmitters to a single high power transmitter. So yes, that is a true statement. Instead of having a single high power transmitter, we have a multiple low power transmitter with the concept of cellular communication. Now, going to the next question. Why the neighboring stations are assigned different group of channels in cellular system? Okay, so let me tell you what is the neighboring stations. So you have one cell A, then you have another cell, then you have another cell, okay, and so on. Okay, so suppose you have neighboring stations. Okay, so this will have a group of channel, this will have another group of channel. So suppose if the channels used by A and channels used by B are same, then what happened? There will be chance of interference. Okay, so if different group of channels are assigned to the neighboring stations, the advantage will be, yes, your answer is right, to minimize the interference. Okay, now the next question, what is a cell in a cellular system? A group of subscribers, a small geographical area, a large group of mobile systems.
Madam, cell means the base station only, no? One base station.
One base station which is controlling multiple users or which is giving access to multiple users. So
They will tell a group of subscribers, madam.
You can say instead of having a big city, it's a small geographical area. So in a large city, a group of subscribers will come in one cell. I mean, the subscribers will come in one. Suppose you have a small group, it's a group of subscribers, we can say like that. But in the concept of cellular communication, you have a large geographical area. Okay, suppose I take it like a city or something. That city is being divided into small cells or small geographical areas. So this cell is actually representing that geographical area. So that is why we call it as a small geographical area. Okay. Now the question is about a concept called as frequency reuse. So let me, before going to that question, I would like to tell, suppose there are some adjacent cells, cell A and cell B. Okay. So there is another cell which is also A. Okay. What does it mean? This cell A has some number of channels, a group of channels. this is being given with channel number 1 to 7. Imagine this has been given channel number 1 to 7. B has channel number 8 to 14 and C has channel number 15 to 22. Suppose again there is a repetition of the cell A, so it will use the same channels 1 to 7. Okay, what do you mean by this? The same frequency channels are being used by this cell and this cell. Okay, so there is a frequency reuse. Okay, now the same channels can be used provided the distance between these two are properly designed. Okay, so what is frequency reuse? Is it process of selecting and allocating channels, process of selection of mobile users, process of selecting frequency of mobile equipment, process of selection of number of cells? So what do you mean by frequency reuse? I'll tell you once again. It is the process of using the same radio channels or radio frequencies on in a site within in two different sites within a large geographical area. So this will be separated by a particular distance so that there will be minimum interference. Okay, so this is having, so in case of frequency reuse, what is happening? This cell and this cell is being allocated with some channel, say 1 to 7. Okay, and again the same set of channels is being given or selected by the next cell also. So this is a process of selecting and allocating the channels. Okay, what do you mean by mobile users? Mobile users are somebody who uses the same cell. Okay, suppose when I say mobile user selection, so all these mobile users will have the same cell, which is giving them the access. Okay, when they are static, when they are moving to another cell, then they will have a different base station connectivity. Okay, so the concept of frequency reuse is, it is the process of using the same radio channel for two different cells within the same geographical area, but the distance between those two cells will be designed such that there will be minimal interference. Okay, so that is what I wanted to convey about the frequency reuse. Now let's move to another question. Which of the following is a universally adopted shape of cell? This is a very simple question. Yes, you are right. It's a hexagonal shape. And now comes the next question. What is the main reason to adopt hexagon shape in comparison to square, triangle or circular? Instead of having circular or square or triangular cells, why do you have the hexagonal cells? The reason is largest area. Without missing any of the corners or with minimum loss of say, you can occupy the maximum area within, when we divide it into hexagonal shapes, the largest area can be covered within a particular area. So that is the advantage of a hexagonal shape cell. Now coming to the next question, Which type of antenna is used for center excited cells? Dipole antenna, grid antenna, sectored antenna, omnidirectional antenna. So when I say center excited cell, it means for the base station in general, for base stations, what is the kind of antenna used? So you imagine there are multiple mobile users in a base station. Ideally, everybody should get the same power. Suppose I have all users like this. Okay, everybody is at suppose on a region which is distance r from this. Okay, so everyone will get the same power. Okay, suppose it is radially arranged. Suppose all the mobile users are like radially at the same distance. Ideally, everybody should get the same power. Okay, for that, what kind of an antenna should be used? It should be a omnidirectional antenna. Omnidirectional antenna means which will radiate equally in the uh, horizontal plane. Okay, so that should be the base station antenna should be a omnidirectional antenna, so that multiple mobile users will have the same power if they are located at the same distance from the antenna. Moving on to the next question. What is a cluster in a cellular system? What is a cluster? So cluster is basically a group of cells. So when we say multiple, so this is cell 1, cell B, cell C, cell D. So the whole thing is called as a cluster. Okay. So cluster is a group of cells. Now, there is a small numerical based on cellular communication. A spectrum of 30 megahertz is allocated to a cellular system. Okay, so you have some 30 megahertz total. Okay, a bandwidth of 30 megahertz in total is being given to a cellular system, a big cellular system. Okay, now there are two 25 kilohertz channels. There are basically two channels. I have two channels. Okay, each of them are 25 kilohertz. Okay, so one is 25k. The second channel is also 25k. Okay, to provide full duplex voice channels. What is the number of channels available per cell for 4 cell reuse factor? Okay, I'll tell you the meaning of this last statement. So before that, we have the total bandwidth. Okay, let me write it. Total bandwidth is 30 megahertz. Now the channel bandwidth is 2 into 25 kilohertz, which is 50 kilohertz. Okay. Now you know the total bandwidth, you know the channel bandwidth. So how many channels will be there? Or how many channels are possible? Number of channels will be 30 mega divided by 50 kilo. What will be the answer? Can you please calculate and let me know? Total number of available channels. It will be 600. Okay. Now, this is the total number of available channels. Okay. This is not the final answer. Please remember, what is the question here? 4 cell reuse factor. Okay. So what do you mean by 4 cell reuse factor? This will be reused 4 times. Okay. If we are going to reuse 4 times, what will be the number of channels? Then it will be 600 by 4, which will be 150. Okay. The cell reuse factor. So final number of channels available per cell will be what? The total number of available channels divided by cell reuse factor. That will be 150 channels. Hope this is clear. So the cell reuse factor means it will be reused. I mean the same set of channels will be reused 4 times. Okay, so these are a few questions on cellular communication. Hmm. And some question on satellite communication. I think I don't have a question in particular, but I can give you some brief on satellite communication. So, as you know, in a satellite communication system, suppose you have a user environment wherein you have a voice or data or video, whatever to be transmitted to a satellite. Okay. So this will be collected, and there is a terrestrial interface. That means within the ground, within the terrestrial area interface, either you can have wire or wired connection, or a fiber connection, or a cable connection, whatever may be the guiding medium. We can have this multiple signals being collected, and then there is earth station. Okay, basically the ground station which will connect to the satellite. So this earth station will be sending in the signals to the satellite. So the earth station will generally have parabolic antennas which will have very high gain to transmit the signal to such a large distances. I mean thousands of kilometers away from the earth. You are transmitting the signal to a satellite. So you need large parabolic dish antennas. You might have seen them in the multiple areas. They are high gain antennas such that at least some signal is reaching your satellite. Okay. Now this is your uplink. Okay. And downlink, what will happen? From the satellite, the signal is being sent back to the earth station, and which will be further be processed for as per the need. Now, generally for satellite communication, the frequency bands used are C band, Ku band, and Ka band. You might be knowing, in case of radar communication, you have come across different bands such as L band, S band, uh, C band, and X band. Okay, so these are like 1 to 2 gigahertz. This is like 2 to 4 gigahertz. This is like 4 to 8, and this is like 8 to 12. So these are all different frequency bands used in a particular communication. Okay, so these are some of the bands used in radar. And what I had been talking about the satellite communication, these are in this range of frequency: C band, Ku band, and Ka band. Okay, so these are all in the range of high frequencies. And you should be knowing something about the carrier to noise ratio. So it can be written as effective radiated power EIRP multiplied by lambda by 4 pi r the whole square into GR by L KTS B. Okay. So the carrier to noise power ratio. Okay. Now you know what is noise power. Okay. KTB. And what is carrier power. Okay. So that is being, this is the ratio. So this, if you notice, for high frequencies, what will be this? Wavelength will be less. So the carrier to noise ratio will be improved. So that is one of the reasons why this we use the high frequencies for the satellite communication. So these are some of the things which I wanted to convey. If there are any doubts with respect to the week 12, you can ask.
Hello, madam.
Yes, please.
Madam, this class no problem, madam. Clear, but that you told no, madam, that revision class. That class I need for that filters, madam. That filter is there, madam. That filter next Monday I need, madam.
Okay. Okay. I will look into
Okay.
those topic. So
Okay.
can you tell me the week number? That will be really helpful.
1 second, madam. I will note down. Just 2 minutes, madam.